Hey class, and welcome back to Prelab number 7. Let's go over these questions for you. So Prelab question number 1 asks us for the conditions of equilibrium of any object that is in equilibrium, any object in rigid body equilibrium. So those are our three basic equations for, again, looking at forces and torque. So the first is that the sum of the forces in the x direction is equal to 0. The second is the sum of the forces in the y direction is equal to 0. And then the third is the net torque about really any axis of rotation is equal to 0. You can summarize these first two as just saying the net force as a vector is equal to 0. That would also work as well. And you could make this a vector as well. Any combination of those would be the correct answer for the first question. Now, the second question asks us to figure out or to think about how we would go about finding the center of mass of a meter stick. So here I have a ruler instead of a meter stick just for the sake of distance, but how would you go about finding the center of this? I'm sure you would probably deduce, since it's probably more or less symmetric, that it would be approximately at the middle. So for a meter stick, it'd be at the 50 centimeter mark. For my ruler here, that's about 12 inches. It'd be more at the 6-inch mark or the 15.5 centimeter mark. But how would you find that experimentally? One option would be to hang it and actually hang it from a couple different points, make vertical lines, and where those lines cross would give you the center of mass. But another easy way is to just balance it. It will naturally balance about its center of mass. And what a cool trick you can actually do with a meter stick, you can bring your fingers in and they will naturally just come together. I'm just pushing my fingers towards each other. They'll naturally come together at the center of mass. And so again, you can just naturally try to balance it, and wherever it will balance is the center of mass. Anywhere off of that, and it won't balance. So that's a fun little trick, bringing the fingers together and then balancing it. And technically, you'd have to balance it this way to find the exact center of mass on this axis as well. But again, we're mostly just concerned with the center of mass along this axis in this lab. So again, the center of mass should be about at the 50 centimeter mark or the 0.5 meter mark, and you just balance it to figure out where the center of mass is. So now we move along to pre-lab question number 3. I have an image here showing the setup from the picture in the lab. I'm using the subscript S for the stick or the meter stick. So again, in the picture, I think it just uses a W, but I'm going to use mg, the mass of the meter stick times gravity. And we're given R1 and R2. To complete our free body diagram, we actually need one additional force, and that's the normal force here. There's a normal force pushing up on the meter stick at the location of the pivot. In addition, we're asked to find the location of the pivot. So what I'm going to do is I'm going to add one more thing onto my drawing here. So if I extend these kind of lines, I'm going to think about this again as a meter stick. So here's the 0 point, here's the 1 meter. So like, for example, if I had something hanging out here, I called this, X3 or something, that would be something like 0.85 meter mark. So I'm going to put X's on here to represent like the physical location on the meter stick of each thing. I'm going to call this X1. I'm going to call this location up here XP, the X location of the pivot, and this I'm going to call XCM. So for example, in this setup, with the way it's looking, X1 might be about 0.02 meters, the 2 centimeter mark. XP is going to come out to be somewhere in this drawing again about the 0.2, 0.25 meter mark, and then XCM is about 0.5 meters. So those are the physical locations on the meter stick. That's going to come in handy when we solve for the pivot location, which is what we're trying to verify in this lab. So moving on to the questions, it asks us to first write out some of the forces. So if we did sum of the forces in the X direction, we know that equals 0. There's no forces in the X, so 0 equals 0, and we get a fun little smiley face. And then similarly, we have sum of the forces in the Y direction equals 0. And in the Y direction, we have the normal force going up minus m1g going down minus the mass of the meter stick times g going down equals 0. So those are some of the forces, and then asks us to also write out some of the torque. So I'm going to do some of the torques. Now it's really up to us to choose an axis of rotation because the net torque should be 0 about any axis. Since we're in equilibrium, I'm going to choose the pivot as my axis of rotation. So again, this is my axis point. So when I do some of the torques, I'm going to have a torque from M1, which is going to cause counterclockwise rotation. So that's going to be a positive torque. So it's going to be M1G, force times lever arm. And in this case, the R1 distance is the perpendicular distance to that force, to the line of action of that force. So that's, again, M1GR is the torque from the first weight force. And then we're going to have a negative torque from the weight of the meter stick, because that's going to cause clockwise rotation. And that's going to be the mass of the meter stick times G times R2. And again, summing the torques equals 0. So now that's really what the question asks. And then it takes it one step further and it says, hey, can you find an equation for this point? Because that's what you're going to actually need in the lab. So this last part that I'm going to go over is going to be really helpful for you to get your actual data, because you're going to predict where the pivot should go and then calculate it and see how that compares to your actual experiment. And you should have very small percent errors. So to do this, I'm going to create just a little more space for myself by sliding over. If I notice on here, this distance right here is R1. Maybe I'll switch colors just to make it a little more vivid here. So here's R1. If you notice, R1 is some number that's just the distance between XP and X1. So if XP is 0.2 and X1 is the 2 centimeter mark, 0.02, then R1 is just 0.18, right? Similarly, R2 is just going to be the center of mass where this forces here, and the pivot location, minus XP. So I'm going to come down and plug those into my equation for torque down here, but I'm going to start by actually canceling out, dividing through by gravity, because the gravity can cancel. 0 over G is still 0. And so now I have M1 times R1, which is now XP minus X1, and then minus the mass of the meter stick times R2, which is X center mass minus XP, and that all equals 0. So now what I can do is I can distribute and really just do algebra to solve for XP. Just to show you, I'll do one more step. M1 XP minus M1 X1 minus the mass of the meter stick times XCM, and then minus a negative, so that becomes a positive mass of the stick times XP equals 0. So I'm going to leave the things with XP on one side and actually factor that out. So I get M1 plus the mass of the stick times XP. So again, I just took this term and this term. And then on the other side of my equal sign, I'm going to move what had negative signs, which are these two terms here, M1 X1 plus the mass of the stick times X center mass. So now I'll just solve for XP by dividing by this term here. So XP is just equal to M1 X1 plus the mass of the meter stick times the physical location of the center mass on the meter stick divided by M1 plus the mass of the meter stick, which this equation should actually look kind of familiar. It looks an awful lot like the center mass equation. So that's the answer to pre-lab question number 3. Pre-lab question number 4 is quite similar. So I have this kind of set up for you already. The only difference is now we're adding a larger mass on the right hand. So again, we're going to have a similar scenario, only now we still have R1, which is still going to be XP minus X1. We still have R2, but now since the pivot's to the right, further down the meter stick, that's going to be XP minus XCM. And now we have R3 added in here, which is going to be X2 minus XP. So our first two sum of the forces equations look very similar. So I'm just going to pop these up here for us. So again, sum of the forces is 0, some of the in the X are 0, some of the forces in the Y are 0. And so I just did some of the forces in the Y. Normal is up, the other 3 forces are all down. And then we're going to do some of the torques, again, similar to how we did it last time. If we choose the pivot as our axis of rotation, we'll have a positive torque from M1, which is going to be M1G R1. We're going to have a positive torque now from the meter stick, since it's on the right and would cause counterclockwise rotation. So we got mass of the stick, G R2, and then we have a negative torque from mass number 2, which is going to be M2G R3, and that all equals 0. So if I divide through by G's, I can then plug in for my R values. So I have M1 times R1, which is XP minus X1, plus the mass of the stick times R2, which is xp minus x center mass, and then minus m2 times R3, which is x2 minus xp, and that's all equal to 0. So once again, you can do algebra. I'm going to skip the algebra for the sake of time, but I trust your ability to do algebra, and you should get xp equals m1 x1 plus the mass of the meter stick times x center mass plus m2 times x2, and then all divided by the net mass of the system, m1 plus the mass of the stick plus m2. So again, this is the equation you're going to be testing in this lab. So we're almost done. However, there's just one more question left. So here's my drawing of the picture that we see in the lab for this pre-lab question. And this one's a little bit easier. I go easy on you here at the end because it just asks you to write out some of the torques and then solve for F, but it lets you do it in terms of R1 and R2. So again, if we're doing some of our torque about the pivot location, which is the pencil here, this is our pivot location, then there's really just two torques. There's mg from the weight on the left times what's now called R2, and then there's minus the force being pulled down by your force sensor times R1, and that's it. So those are our two torques. And so to solve for F, you just do FR equals mg R2, that's R1, divide by R1. So the force should just be mg R2 over R1. Boom, Foxworthy. So again, in this lab, you're going to be testing each of these three different equations we just derived. You're going to be testing that one for F. You're going to be testing this pivot equation here and this pivot equation up here, all in the course of today's lab. So I hope that helps you. Hopefully you got all of that information. You can always go back and rewatch this if needed. But again, you'll be testing those three different equations, so make sure you have them right so you can get accurate theoretical values in today's lab in order to get those nice low percent errors you should see for today. So if you have any questions, as always, shoot me an email or let me know. Otherwise, have yourself a box-worthy day. Boy, howdy, have fun.